Hello everyone. This is the training about Eigenvalue, one of the Midas training series. I hope you enjoy this training. Why do we need dynamic analysis? It is because the loading on the structure is not static. The magnitude and direction of loading change with time like earthquake loads. In the static equilibrium, we just consider externally applied loads and internal forces carried by the structure. What other types of forces should we consider in the dynamic equilibrium? There are inertia forces and damping forces acting on the opposite direction of external loads like this. The inertia force is determined as the product of mass and acceleration, and the magnitude of damping force is proportional to the velocity of the vibrating mass. We need to know more about the damping. What is damping? The process by which free vibration steadily diminishes in amplitude is called damping. In damping, the energy of the vibrating system is dissipated by various mechanisms. In a vibrating building, the energy dissipation arises from the inertia friction when structural members are deformed. Also, friction at steel connections, opening and closing of microcracks in concrete, friction between the structure itself and non-structural elements contribute to the energy dissipation. The damping of a structure without any added dampers is called inherent damping. It is impossible to describe mathematically this inherent damping. So, damping coefficient is generally determined from the damping ratio using this formula. The damping ratios are typically assumed to be 3% for steel structures and 5% for concrete structures. Let's consider the dynamic equilibrium for earthquake loads. The earthquake loads are applied to the support of the structure. The support of structure is shaking along with the ground motion. So, the displacement, velocity, and acceleration of structure include the ground motion. While both damping forces and internal forces carried by structure arise from the relative response, the inertia forces are caused by absolute acceleration. So, the equation of equilibrium will be like this. No external load is applied on the structure except for support. But for practical purpose, we usually use the next equation. Here, the inertia force by ground acceleration is moved to the right side. This inertia force by ground acceleration is called effective earthquake load. Let me show you how dynamic equilibrium is satisfied in case of earthquake loads for the single degree of freedom system. In this example, mass, stiffness, and damping ratio are given like this. In Midas, the unit of mass data is force per g. Here, g does not represent gravitational acceleration. Instead, it takes just the unit from the gravitational acceleration. As for the damping coefficient, it can be obtained from the damping ratio using this formula. The effective external load can be calculated like this. The load varies with time. We will check the equilibrium at the time of 2.16 seconds. Make sure that the ground acceleration data here is normalized by gravitational acceleration. So, the ground acceleration should be obtained by the product of the function value and gravitational acceleration. By performing time history analysis, we can obtain relative displacement, velocity, and acceleration at the time of 2.16 seconds as shown here. As shown here, we can see that the dynamic equilibrium is satisfied in this example. In static analysis, the magnitude of applied loads affect the magnitude of displacement. In dynamic analysis, not only the magnitude of loads, but also the speed of loading or the frequency of loading affects the displacement. When the frequency of load comes near to the frequency of natural mode, the displacement becomes larger than static response due to dynamic amplification. When the frequency of load is very low or slowly loaded, the response is almost the same as static response. If it is very rapidly loaded, the displacement becomes zero. If there is no damping in the structure, the displacement at resonance will be infinite. In the previous slide, we learned how the frequency of loading affects displacement in the SDOF system. Now we will see how the displacement can be determined from inelastic MDOF system based on the frequency of loading. As shown here in this image, the displacement of MDOF system will be determined by the combination of displacement of mode 1 and mode 2. In this case, as the frequency of loading is closer to the frequency of natural mode 1, the contribution of mode 1 will be larger than mode 2. Once we know the displacement of each natural mode of MDOF system, we can determine the displacement of MDOF system. Now, we wonder how MDOF system can be decomposed into several SDOF systems which correspond to natural modes of MDOF system. We can do that with eigenvalues and eigenvectors of natural modes. In order to determine the actual displacement of MDOF system, the displacement of each natural mode should be multiplied by the mode shape of the corresponding mode. We will see this in details in the next example. Here we have an example of 3 DOF system. The mass matrix and stiffness matrix are like this. If we apply dynamic equilibrium at the 3 different levels, the equations are coupled with each other. This building has 3 natural modes. Frequencies and mode shapes can be obtained by solving eigenvalue problem. By using eigenvalues and eigenvectors of 3 natural modes, 3 uncoupled equations of motion of SDOF systems are obtained here. The displacements of each floors are obtained by the product of the displacement of SDOF system and the mode shape of each floors. Finally, the displacement of MDOF system. For example, the displacement of the first floor, U3, can be obtained by the linear summation of modal displacements as shown here. Other responses like base shear, element forces can be obtained from the calculated displacements. In the uncoupled model equations, the mass of each SDOF system is 1.0, and the ground acceleration is scaled. The scale factors is 1.425 for mode 1 in this example. The scale factor to ground acceleration for each model is called modal participation factor. For the time history analysis of SDOF system, the ground acceleration should be scaled by this factor. And for the response spectrum analysis, the maximum displacement obtained from response spectrum function should be scaled by this factor. We'll see this in the response spectrum training. The values of modal participation factors change depending on the scaling of mode shape or how mode shape is normalized. Typically, two methods are used for the scaling of modes. The mode shape can be scaled with reference to the mode shape of top floor, or it can be normalized by mass matrix. The values of modal participation factors are different between different unit settings. In Midas, the modal participation factors are calculated based on the unit setting at the time when the analysis is performed. After analysis, the calculated modal participation factors will not change although different units are selected by the user. If you need to see the correct values of modal participation factors, you should perform analysis again after changing the unit system. The sum of the effective modal mass for all modes is equal to the total structural mass. The value of effective modal mass is independent of mode shape scaling. We should use enough modes in the analysis to provide a total effective mass not less than 90% of the total structural mass. Also, the effective modal mass for each mode is used to calculate the base shear for each mode in the response spectrum analysis. We will see this in the response spectrum training. Why do some engineers want to use Ritz vector method instead of Eigenvector method? Eigenvector method always provides exact frequencies and shape of natural modes. This is a model of lightweight superstructure built on a massive foundation supported on stiff piles that are modeled using a spring. This structure has 5 natural modes in the lateral direction. These are exact results for frequencies, periods, mass participation, and mode shape, which can be found by including all 5 modes in the eigenvalue analysis. Even though we do not include all 5 modes, for example, we include only 3 modes if we use eigenvector method, still all results for the lower 3 modes are exact results. In the rich vector method, the user should select starting load vector and number of generations. For the earthquake loads, spatial distribution of masses are recommended as the starting load vector. Midas provides three default starting load vectors such as ground acceleration x, ground acceleration y, ground acceleration z, ground acceleration x. Ground acceleration x represents the spatial distribution of mass in the x direction. Number of generations determines the number of modes. With rich vector method, if all 5 modes are included, the results are the same as exact results. If only 3 modes are included, rich vector method does not give exact results as shown here. In this example, the errors in the frequencies are almost 0% in the first and second mode, but 39% in the third mode. And the errors in the mode shapes are almost 0% in the first mode, 7% in the second mode, 11% in the third mode. The third mode is so much in error that it may be useless. The frequencies and eigenvectors are approximations to the natural vibration frequencies and mode of system. The approximate results are generally more accurate for the lower modes and gradually deteriorate for the higher modes. Usually, the second half of the frequencies and modes is not accurate enough to be useful. Thus, the number of rich vectors included should be sufficient to determine accurately the desired number of natural modes. Therefore, it is important to know that rich vector method should not be used for the response spectrum analysis to obtain displacements, member forces, and base shear, because the frequencies and mode shapes obtained from rich vector method are approximate results. It should be used for the time history analysis in which displacements of dynamic equations are obtained using numerical time stepping methods. However, if we include full number of modes in the rich vector method, we can use response spectrum analysis because the approximate frequencies and mode shapes are almost same as their exact values. What will happen if we change starting load vector to a static load applying only to the foundation level and include only 3 modes? Frequencies and mode shapes are still different for the first and for the third mode, but the mass participation percentage is almost 100%, although only 3 modes are included. Let's see the response of structure obtained from the time history analysis in the next slide. Actually, the response of structure are important for engineers rather than mode shapes. In this graph, the base shear forces are compared between rich vector method and eigenvector method. As you see here, the base shear forces by rich method are almost same as the exact results, but the result by eigenvector method are much smaller than the exact results. We can say that If the same number of modes are considered, the rich vector method gives more accurate results than eigenvector method. In this bridge, viscous dampers are installed. The bridge will be deformed in a linear elastic range, and the dampers will undergo nonlinear behavior when subjected to earthquake. This system can be solved by nonlinear model time history analysis, which requires model analysis. The previous of vibration of damper is small compared to the response of structure. Also, for a certain type of building structures, it is necessary to calculate the vertical dynamic response. In some cases, several hundred modes are necessary in order to obtain the 90% mass participation in the vertical direction. These are another examples showing that using eigenvector method is not so efficient in terms of computation time and computer storage requirements. This is all for the training. Thank you for listening.